Welcome to 2.5, which covers solutions by substitutions. Okay, so we've learned 3 solving methods so far. So before we jump into substitutions, let's make sure we remember the solving methods that we've done so far. As I've said in this class, we're going to be continuing to build on and add on more and more different solving types. If you have not started one already, I would highly suggest that you start a list of all the solving methods that we have covered. This could be the start of your list. The first method we looked at is we looked at separable equations, or separation. We also looked at linear equations. So those were the ones of the type a1 of x dy dx, add a naught of x times y is equal to g of x, and you found mu of x, the integrating factor. And then the last type we've taken a look at are exact equations. So that was m of xy dx, add n of xy dy is equal to something, and we said m of y should be equal to n of x. That proves that the equation is exact, and then the exact equation is the one that is similar to finding a potential function. Okay, so those are the 3 that we've covered so far. What we are going to be covering today is substitution. And so the idea is that we want to take a differential equation and transform it into a differential equation of another type, one that we know how to solve. So suppose that we have some dy dx that is f of xy. We might want to substitute in something. So maybe we want y to be a function of x and u. So differentiating that equation that I just underlined, the derivative of y with respect to x would be the partial of g with respect to x, dx, which is just 1, so you don't need to write that, and then the partial of g with respect to u, du dx, which can be written as partial of g with respect to x in terms of x and u, add the partial of u with respect to x and u, du dx. Okay, so at this point then, we're going to go back to the original differential equation that we had above. For du dx, we're going to replace that with the expression that we just found. So our du dx, we get gx of xu, u, add gu of xu, du dx. And that is now equal to f of x, and y we are replacing by g of xu. So what we get then is we get du dx is some function of x and u. And notice I used a capital F, not a lowercase f, so it is different than this function we have above. So the question is, can we solve that equation? And ideally, we're going to be able to. So there are 3 different types of substitution that we're going to look at. We're going to look at homogeneous equations, Bernoulli equations, and then that third one you see dy dx is some function f of ax add by add c. So we're going to start with homogeneous equations. Okay, homogeneous. If a function has the property that f of tx ty can be written as t to the n times f of xy for some n that's an element of the real numbers, then we say that f is a homogeneous function of degree n. Okay, so let's take a look at this example. First thing we're going to want to know, is this homogeneous? So I'm going to find f of tx and ty, and this is 3tx squared, subtract 5tx ty, add ty quantity squared. So this is, if I factor out a t squared, I'm going to end up with 3x squared, subtract 5xy, add y squared, which is t squared multiplied by the function in terms of x and y. So this tells us, yes, our function is homogeneous. of, we say degree 2. Okay, and just a fun fact for you to write off to the side. If your function is homogeneous of degree n, so in this case degree 2, we can write the function as the following. So we can write f of x, y as x to the n times f of 1 comma y over x. Or we can write y to the n times the function of x over y comma 1. So we don't need that now, but it might be helpful to us later. Okay, a little bit of a tip on the next page before we move on to a definition. A function is homogeneous. Well, that's definitely not spelled right. There we go, homogeneous, if all terms have the same degree. So for example, if I'm looking at f of xy is equal to x to the third add y to the third, right away you can tell that this is homogeneous of degree 3 because all of the terms are third degree. And then if you were to check and go through the same process we did before, we would get tx to the third add ty to the third, which can be written as t to the third x cubed add y cubed. Okay, so that leads us to our next definition. A differential equation of the form m of xy dx add n of xy dy equals 0 is homogeneous if both coefficients m and n are homogeneous functions of the same degree. So m and n have to be homogeneous functions of the same degree. If they do, then our claim is that if you substitute u of xy, or x is equal to vy, that will reduce our equation into one that we can solve using separation. So I know what you're probably thinking. Mrs. Needham, am I just supposed to blindly trust that that's the case? No, of course not. Let's prove this. So let's start with the equation that we wrote above. We have m of xy dx add n of xy dy is equal to 0. And we're going to make some substitution. So I'm going to choose to make the substitution y is equal to ux. So if I do that, in the equation above, I'm also going to need dy. So dy would give us u dx add x du. So if we substitute, we're going to get m of x comma u of x dx add n of x u of x, and then u dx add x du is equal to 0. Now remember, we are assuming from above that m and n are homogeneous functions of the same degree. So since m and n are homogeneous of the same degree, and that's something really I should have written earlier that we're going to assume, we are going to rewrite that equation as follows. So we will write this as x to the n times m of 1 u dx add x to the n of n 1 u dx add x du is equal to 0. To assist us, I'm going to number these steps so you know where I'm going with this. So then our next step, what we're going to do is we will divide by that x to the n. So when we do, we're going to have m of 1u dx add n of 1u dx add x du is equal to 0. So when we do proofs, now might be a good time for us to just take a pause and remember where we're trying to get to. We are trying to prove that this equation that we started with, we can bring this into a separable equation. So the next thing that we're probably going to want to do is factor. Okay, so I'm going to have something multiplied by dx, and then I'm going to have another something multiplied by du is equal to 0. If I take out all of the dx terms, I have m of 1u add n of 1u times u, and then I'm going to have n of 1u times x du is equal to 0. This is now separable. So we're going to move around some of our displaced terms. Okay, so I'm going to move my du to the right side, so I have all my x's on the left, all my u's on the right. So I'm going to have dx over x. And then for the du, I'm going to have negative n of 1u over m of 1u add n of 1u u, all of that du. This we can now solve by separation. Just so you know, you also might see those terms written on the same side. So you might see it written like this. Either one works, either one is a separable equation. Okay, so let's take a look at an example. So here's our example on the next page. As a reminder, when you are solving differential equations, you should always be going through a mental list of how do I know how to solve equations. Can I solve by separation? Is the equation linear? Is it exact? And now we're adding on homogeneous, or solving by substitution. So when you get to the test or when you get to your final exam, you're going to be tested on all of these together. So it's going to be important that you're able to differentiate between the different methods of solving. Okay, so obviously we know we're going to try to solve this by substitution and have it be a homogeneous equation. So in this case, we have degree 2, degree 2. So yes, this tells us we have a homogeneous equation of degree 2. Okay, so we can do either y is equal to ux, which is what we did in the proof, or we can have x is equal to vy, either one. We're going to do the u one again. So if we let y be equal to ux, our dy then would be u dx, add x du. Okay, so we're going to substitute all of that into our original equation. So when we do, we're going to get x squared add, replacing that y, we're going to get u squared x squared dx. We then have x squared subtract u x squared times u dx, add x du is equal to 0. And then if you remember, the next thing we did is we divided by x squared because we're of degree 2. So we then have 1 add u squared dx, add 1 subtract u dx, add x du is equal to 0. Now is when we want to factor or group, make sure we get everything with dx together and everything with du together. So if we get our dx's together first, we have 1 add u squared, add 1 subtract u times u dx, add x multiplied by 1 subtract u du is equal to 0. So simplifying this right here, we get 1 add u dx, add x 1 subtract u du is equal to 0. All of that was to get us in a position where we can now separate. Okay, so if I get my u's together and my x's together, I'm going to write everything on the same side. So I get dx over x, add 1 subtract u over 1 add u du is equal to 0. And then I'm going to integrate. So I'm going to get natural log of the absolute value of x. And then I got to figure out how am I going to integrate this u term? Well, you're either going to have to do long division or synthetic division to simplify that fraction. So if I take negative u add 1 and I divide it by u add 1, so I'm going to end up with a negative 1. So that's negative u subtract 1. If I subtract, I get 2. So there's a remainder of 2. So that is the same as negative 1 add 2 over u plus 1. So that is really what I'm going to be integrating. When I integrate that quantity in yellow, I get negative u add 2 natural log of u plus 1, and all of that is equal to some constant. Okay, so then what I'm going to do, I'm going to put u to the other side. So this will be the natural log of x u add 1 quantity squared is equal to c add u. And then I'm going to get rid of that natural log. So I have x multiplied by u add 1 squared is equal to c e to the u. So this c, I'm going to mark c1, and then e to the c just gives us a different constant. Okay, so then remember, we've solved, but we need y in our equation, not u. So if we remember, we made y be equal to ux, so u then is y over x. So I'm now going to replace these u's. So this gives me x, y over x add 1 quantity squared is equal to c2e to the y over x. Now, you can probably tell that we're not going to be able to express this explicitly. We're only going to end up with an implicit solution. So it is perfectly fine to leave your solution like that. Oftentimes what will happen is we will simplify this left side so we don't end up with that fraction y over x. So if you wanted to simplify a little bit more, this is the same as x multiplied by y add x over x quantity squared. The right side stays the same. So this is y add x squared over x. Right side stays the same. Or y add x squared. If I multiply by x, I would get c2x e to the y over x. So that is another way of expressing the solution. Okay, so you might be asking, how do you know when you should use y equals ux or x equals vy, right? How do you know which substitution to do? In general, you're going to use you're going to use y equals ux when n is nicer or less complicated, and you're going to use x equals vy when m is nicer or less complicated. Sometimes you're not going to be able to integrate after one substitution. So in the previous example, if we had used x equals vy instead, maybe we would have been able to integrate, maybe not. So that's something that you might find is you try an integration and it doesn't, or you try a substitution and it doesn't give you a separable equation, so then you might have to do the other substitution. So let's take a look at one more example of this type. Okay, so looking at an example like this, here is my thought process. First of all, is it homogeneous? Well, we have degree 4, degree 4. So yes, this is homogeneous of degree 4. So you're going to ask yourself, which of those terms that I underlined looks less complicated? Well, this first quantity only has one term. This second quantity has two terms, so we're going to use the first one. One term is generally less complicated than two terms. Because it has a dx, we're going to use the x substitution. So x is equal to vy, which means dx then is v dy, add y dv. At this point, I would suggest that you try this problem on your own, that you pause the video, do those substitutions, and see if you can get down to something that's separable. When you're ready, come back and we'll go through it together. Okay, so hopefully you tried that one on your own and you didn't just keep watching. So let's see how we did. We end up with 2 vy cubed y, and then dx is v dy, add y dv. We're adding vy to the fourth, add y to the fourth. all of that dy is equal to 0. Okay, so we know because we're of degree 4 that we're going to have to divide by y to the 4th. So when we do that, we're going to have 2v cubed times v dy, add y dv, add v to the 4th, add 1 dy is equal to 0. So then we're trying to get our dy's together and our dv's together. So we're going to have 2v to the 4th, add another v to the 4th, add 1, all of that multiplied by dy. And we're going to have 2v cubed y dv is equal to 0. Okay, so then getting our v's together and our y's together, we're going to have dy over y. And then I will have 2v cubed over 3v to the 4th, add 1, dv equals 0. Okay, so this now we can solve by separation. So we're going to integrate. So we get natural log of y, add. Okay, you might be able to do this integration in your head, or it might be helpful to write a little work off to the side. If our u is 3v to the 4th, add 1, our du then would be 12v to the 3rd dv. So when we integrate, that's going to give us 1/6 natural log of 3v to the 4th, add 1, equals some constant. Okay, get those two natural logs together, condense them, and then apply an e, and we would end up with y multiplied by 3v to the 4th, add 1, to the 1/6 power is equal to some constant, and that is just e to the c1. And so then continuing my work, at this point, I'm going to replace this v back. So all the way up here, I know that v is equal to x over y. So if I substitute that back in, I'm going to have y times 3 x over y to the 4th, add 1, all of that to the 1/6 power is equal to c2. So I'm going to look to simplify this stuff in parentheses. So this is y 3x to the 4th, add y to the 4th, over y to the 4th, all of it to the 1/6 power is equal to c2. So then if I take everything to the 6th power, I'm going to get y to the 6th times 3x to the 4th, add y to the 4th, over y to the 4th is equal to c3. And of course, c3 is just c2 to the 6th. And then a little more simplifying, I end up with 3x to the 4th y squared, add y to the 6th is equal to c3. So if you did in fact try this problem on your own, I hope you were successful, or at least that you were on the right track. So that is the first type of substitution. Just a few quick notes for you at the bottom before we move on to the second type. You will also need to find c. So those are our initial value problems. And then one thing to just be careful of, I would be careful with the ordering of the equation and make sure that the equation has dx then dy. That helps me keep things a little bit straighter in my mind when I'm doing my substitution. So for example, if I have this equation, first thing I'm going to do, of course, is get everything together on that right side in one fraction. So when I do, that gives me x to the 3rd, add y to the 3rd, add xy squared over xy squared. So then, when I cross multiply and get my dx and my dy together, I try to lead with dx. I forgot my dx. because I can very clearly tell that n is the less complicated term, and so I know then that I'm going to use y is equal to ux. Now, of course, like I showed you earlier, the other way to think about it is just look at the dx and the dy part. dy being less complicated, substitute for y. So that is the first type of substitution, homogeneous equations. Next type that we're going to look at is Bernoulli. Second type of equation we are going to solve by substitution is a Bernoulli equation. A Bernoulli equation is of the form dy dx is add p of x multiplied by y is equal to f of x times y to the n. And so this should look pretty familiar. This is similar to a linear equation, but it has this extra factor. And that's that y to the n. And so again, the idea is that we're going to solve this using substitution. And what we're going to do is we are going to use the substitution w is equal to y to the 1 minus n. So we're going to go through the general derivation and then we'll look at an example. So first thing that we're going to do is we're going to differentiate with respect to x. So when we do that, we get dw dx is equal to 1 subtract n y to the negative n dy dx, which gives us then dy dx is equal to 1 subtract n to the negative 1 y to the n dw dx. Okay, so we're going to see how that's going to help us. If we go back to this equation, our dy dx, now we're going to replace all of this for dy dx. So we get dw dx, 1 subtract n to the negative 1, y to the n, add p of x multiplied by y is equal to f of x times y to the n. So we're going to divide by that y to the n. So when we do, we get dw dx multiplied by 1 subtract n to the negative 1, add p of x times y to the 1 minus n is equal to f of x. And so initially you might be thinking, well, why is that helpful? Well, this y to the 1 minus n, we defined that as w above. So that's really w. So then, once we make that a w, we are also going to divide by this term so that we can put it in linear form. So I'm going to do both of those in the same time. So I'm going to divide by that 1 minus n, and I'm going to replace that y to the 1 minus n with a w. So we get dw dx, add 1 subtract n, p of x times w is equal to 1 minus n f of x. Now we are in linear form, linear in terms of w. So we're going to solve for w, right, solving the linear equation, and then we will substitute back at the end. Now that we have the basic idea, let's take a look at the example. Okay, so here is our Bernoulli example. First thing that you're going to do, of course, like we have with the other examples, is consider some other options. Is this separable? No. Is this linear? No, because of that y squared. Is it exact? No. Okay, so last option. Well, not last option, really, we could check that it was homogeneous first, which it's not. So now we're going to consider Bernoulli. Okay, this is the structure of Bernoulli, right? This equation looks almost linear, except that we have that y squared. Okay, so since it's Bernoulli, we're going to let w equal y to the 1 minus n, which in this case is y to the 1 subtract 2, or y to the negative first. So our w is y to the negative first. Our dw then is negative y to the negative second dy dx, which tells us then that this is dw dx. So our dy dx then is negative y squared dw dx. Okay, so now we are going to return to our equation, and we're going to do some substituting. So we get negative y squared dw dx, subtract y is equal to e to the x y squared. Because of this y squared, we're going to have to divide out the y squared. I'm actually going to divide out a negative y squared so that I get a lead coefficient of 1. So when I do, I get dw dx, add y to the negative 1 is equal to negative e to the x. Now, if we've done everything correctly, this term right here should end up being w, which it is, because then we are done with all of our y's. So we have dw dx, add w is equal to negative e to the x. So all of that substituting was now to get us to a form where our equation is linear. So that's what we're going to do now, treat this like a linear equation. So we're going to start by finding our integrating factor, which is e to the integral dx, which is just e to the x. So we're going to multiply our entire equation by e to the x. On the left side, we would end up with e to the x multiplied by w, the derivative of that. And then on the right side, we're going to get negative e to the 2x. So we'll integrate. Left side, we get e to the x multiplied by w. Right side, we get negative 1/2 e to the 2x, add c. Okay, this might be a good place for us to replace that w. So we get e to the x multiplied by y to the negative first is negative 1/2 e to the 2x, add c. So we get y to the negative first then is negative 1/2 e to the x, add c e to the negative x. And finally, our answer ends up being y equals 1 divided by that negative 1/2 e to the x plus c e to the negative x. Okay, I have a quick note for us, so please make sure you write this down, and then we will move on to our last kind of equation. So quick note is please make sure that you are careful with your substituting. Let's consider this equation. dy dx, add x squared y is equal to x to the third over y squared. What is w? Well, our w, so y to the 1 minus n, is going to be y to the 1 subtract negative 2, or y to the third. So just remember, when you have in the denominator, we're going to use a negative exponent. Okay, so that was our second type. On the next page, we're going to do the last and final kind of substitution. Last substitution type is the one you see at the top. dy dx is some function of ax add by add c. As you can probably guess, your substitution will be u equals ax add by add c. So let's take a look at this last example. dy dx equals what you're given, and this is an initial value problem, so we will need to solve for c. So we are going to let u equal negative 2x add y. du then, dx will be negative 2 add dy dx. So like we did before, dy dx then will be equal to du dx add 2. Okay, so going back to our equation, substituting for dy dx, we get du dx add 2 is equal to u squared subtract 7. So we get du dx is equal to u squared subtract 9. Okay, at this point, this equation is separable, and that is always going to be the case. So now we're just going to solve like we normally would. du over u squared subtract 9 is equal to dx, and I'm going to integrate. Okay, let's see how our integration skills are at this point. Over here, we're going to have to do some partial fraction work. So we get a over u subtract 3, add b over u add 3 is equal to 1 over u squared subtract 9. So I have a multiplied by u add 3, add b multiplied by u subtract 3 is equal to 1. So at this point, you can solve the system. You can choose convenient values, whatever you prefer. So if I choose u equals negative 3, I get negative 6b equals 1. So b equals negative 1/6. Similar idea, I'm going to get a equals positive 1/6. Okay, so where that takes us then, we have the integral of 1/6 over u subtract 3, add negative 1/6 over u add 3. All of that du is equal to the integral of dx. So this gives me 1/6 natural log of u subtract 3, subtract 1/6. Oops, forgot my natural log there. Natural log of u add 3 is equal to x add c. So combining those natural logs, I get 1/6 natural log of u subtract 3 over u add 3 is equal to x add c. Okay, so getting rid of that 1/6 and using an e, I'm going to get u subtract 3 over u add 3 is equal to c1 e to the 6x. Okay, so I multiplied everything by 6, then I applied the e, and so remember that that c1 is just e to the 6c, right? It's just a constant. Okay, so if I want to solve for u then, I'm going to get u subtract 3 is equal to u add 3 c1 e to the 6x. So if I factor out a u and move all the u's to one side, I'm going to have 1 subtract c1 e to the 6x is equal to 3 add 3 c1 e to the 6x. So finally, solving for u, we get 3 add 3 c1 e to the 6x over 1 subtract c1 e to the 6x. Now here is the unfortunate part where I remind you that we're not solving for u. So if we go back to how we defined u, this is really a negative 2x add y. Okay, so where that leads us to then is we get y equals 2x add that fraction. And finally, we have our initial condition. So our y of 0 is equal to 0. So we get 0 equals 0, add 3, 1 add c, all over 1 subtract c. So our c is negative 1. So finally, where that leads us, we get y equals 2x, add, if I factor out a 3, I have 1 subtract e to the 6x over 1 add e to the 6x. Okay, thanks for sticking with me. If you have not started to make a list yet of the different solving methods, I would highly suggest that you do it now because we're going to have more to come. Until next time, thanks for being with me.